All right, so let's start the quiz. Okay, so tips on this quiz. Go ahead and pass it around. A tip on the quiz is, make sure you can simplify it down. But canonical just means like the most simplest form. Just pass it around. So a tip on the quiz. First simplify it, and then, at first, just try to make them equal. Try everything you've learned so far, with the whole multiplying by one thing, and just try to get as far as you can. Thank you. No. I'm just preparing something. When you guys are done, you can come bring them up. And you can pick up your last week's quiz also if you want. You guys almost done? I mean, okay, so you don't need to do any truth tables. You don't need to do anything. It's just algebra. That's what they mean by canonical. It's all the Boolean laws and all the properties and all that. Yeah, no, what's your Christopher Cruz? There you go. Not that many people did well in the last one. Just show as much work as you can. I'm gonna give you guys as much extra credit as you can. Or partial credit. You guys almost done? Mm-hmm. Yeah, no, that's fine. That's fine. Goodman. Probably right there. You didn't take a quiz last week, so you took it in the last section, right? I'll try to get it back from them or something. I don't know, you're probably around here somewhere. I think I just saw you. Yeah, it's just the quiz. I don't have homework. I don't have homework today. Alright, your quiz checker. Who's still taking the quiz? Okay. And you didn't take a quiz this week? Chris Nelson? Yes. Alright. You want to get your quiz back? Here you go. Yeah, I'm gonna talk about that right now. So quizzes, all right, let's have all the quizzes back. Just, I'll give you guys partial credit. It was a long problem, but whatever. It's all good. All right, so first of all, we have all the quizzes back? Okay. All right, so last week's quiz didn't go all that well. So I wanna just say some things about that one. So definitely, you guys should definitely have a few things memorized. So like De Morgan's law, definitely memorize it. So what's De Morgan's law? Who can tell me what De Morgan's law is? Someone other than Ming.
It's like parentheses a plus b prime is equal to a prime b prime.
Yeah. So what would this equal? What would this equal?
It would be a prime b.
Yeah, right. So with De Morgan's law, this turns from an or to an and you prime each thing. So yeah, a prime b. Same thing goes for like this. This will switch over to a double prime plus b prime, which is a plus b prime. So definitely just like, also I was seeing that, I think when in the problem where it asked to expand it out to a product of sums, you guys are trying to use De Morgan's law to open it up, but that doesn't, using De Morgan's law and backwards doesn't really make any sense because it just makes your thing more complicated. You're making it more unsimplified. So it's better to get rid of all the primes, with De Morgan's law, and then use the distributive properties, like the distributive of addition and all that stuff. And for the distribution of addition, it has to do with like what's so it's like B A or B C. This equals. It's like this A is being distributed, like the plus is being distributed to each of these terms. So it's A plus B plus A plus C. And you can work this out, and you can see that does equal AC, AB plus BC. And then this what does this equal right there? That just equals A, right? So you get A plus BC. That's the main thing. All All right. So I want to talk about some topics that are going to be on your homework for over the weekend. So okay, so you guys have done truth tables, and the truth tables just organizes what your function is going to do for a certain amount of inputs, and from your truth table you can get the sum of products and the product of sums, which is the DNF and CNF form. So you can write out expressions for f and for f in two different ways. But that's not usually the most simplified form of writing f, and that's why we use the Carnot map. So the Carnot map, the way the Carnot map goes is that so when you get into like the three-dimensional Carnot maps, which is one on your fourth homework, you have to be a little bit careful on where you place your variables. So if your expression comes in like A, B, C, D, this is the least significant bit. This bit goes 0, 1, and then this is like 0, 2, this is 0, 4, 0, 8. So in this case, I have A, B, C, D, and A, B are the most significant ones, and C, D are the less significant ones. So right here in this combination, A, B is 0, 0, 0, 0. This is 0, and then this is 1 here. This is the 1 point here. Does that make sense? Because it's A, B equals 0, C equals 0, D equals 1. And that's for the 1 term. I mean, like if you go through the lecture notes, you'll be able to spot it. But it's just, you have to be careful. So this is like the 1, this is the 0, this is the 1, this is the 2, because A, B is 0. Here, C, sorry. 0, 1, oh, my bad, I wrote this wrong. This is the 2 point because A, B is 0, C is 1, D is 0. So you have 0, 0, 1, 0, that's 2. 3, 4, 5, 6, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So like, after a while you're going to memorize the order, but that's just really important. When you go into if you have, this is for four variables, right? If you have a fifth variable, like let's say it was A, B, C, D, E, then the way you would organize the Carnot map is you would make one Carnot map. You would make one Carnot map for this, the most significant bit A, being 0. So like A equals 0, and then you would be doing DE and B, B, C, and DE. Kind of the same format as the A, B, C, D. So A, B, the most significant ones were here, and then C, D were here. But now that we have this extra fifth bit, you let A be the other, like the most. A is the most significant. So when A is 0, you have one Carnot map, and then when A is 1, you have the other Carnot map. I mean, if you guys have questions, you guys can come ask about it later. But okay, so we have A, B, C, D, just a simple, four level Carnot map. So we have, there's things called the implicants. The implicants are so you're trying to minimize your expression of f, and the way you do it is by you're gonna try to express each of these minterms, each of these ones with the least amount of literals, with the least amount of variables. And the way you do it is in the Carnot map you draw these implicants. And then the only criteria on the implicant is that the width and the length of it, the multiplication of the dimensions has to be a power of 2. So you can't draw like a 6 square. You can't draw a 6 square implicant because that's not a power of 2. It's not going to work. So like this is fair game. This square here is fair game because it's 2 times 2 is 4. And then this long one is 4 squares, so it's fair game. So when you're doing a Carnot map, there's prime implicants. I mean, here in this case, you want to make your implicants as big as you can. So that's why I made this, 4 square one. I could have made this, 2 square ones, but that's not being efficient. That's not the optimal. And then, the ones that aren't optimal, those are the ones that are known as just the regular implicants, the prime implicants. Let's say I had a 1 here. Or no, let me put the 1 here. This is better. So I have this 4 square here, and then this one. Let me put another one here. Okay, actually, put it here. So to get these 2 bits, I can either put a implicant there, or I can do this, or I could even do this, because the Carnot map wraps around itself, right? So these are all prime implicants. They all work. There's just many combinations. Those are the prime implicants. Yeah.
What is the definition of a prime?
A prime implicant it's the prime implicant is the square. It's maximizing the area of it. And when it's prime, it just means that it's as big as it can get. So like this one is the 4 one that goes all the way across is as big as it can get. I can actually draw another one here, so it's not a great example. But it's really just when she asks you for prime implicants, she's talking about the square, the expression that it closes. So to give you an example, so this one here, this prime implicant, the like algebraic expression for this one would be C prime D prime, because these are the ones that stay constant all across so that's what that is. So this is C prime D prime. This is that prime implicant. That's what it means. So there's a difference between a prime implicant and an essential prime implicant. An essential one is when you have a bit that you can't get to it with any other prime implicant. So like this bit here, the only way I can get to it is if I draw this 1 square implicant here. So that one's essential. That one has to be in your function. Does that make sense? So that's good to keep in mind. You're going to be doing that a lot on your homework. Prime implicants, essential prime implicants, and yeah. So from here, I can get an expression. Let's say it's C prime D prime, and I'm going to get rid of this 1 here. So I'm going to draw this whole prime implicant here, and this one here. So that's C prime D prime. And then this one here is A prime B. You guys see how I got that? It's this column here, the A prime B one. And then this one here, which is going to just be, A, B prime, and then C, D. You guys get how I got those? Yeah? All right. And then from here, we can get the actual circuit. And that's when we use these gates. So we have the NOT gate, the AND gate, the OR gate. They all correspond to each of the algebraic expressions. So how about for this term? What would be like the gate implementation for this term? Who would know how to do this? Anybody got an idea? Yeah, you definitely need an AND gate, yeah, because there's an AND operation. Yeah, so I have 2 inputs, right? A C, D, and then yeah, you want to invert them, and then you AND them. And then over here you have C prime, D prime, right? So what other way could I do this with one of those gates up there? So think De Morgan's law. What other way could I do this? The OR gate? The NOR gate, yeah, exactly, right? Because A, B, NORed, by De Morgan's law gives you A prime, B prime. So this could, very simply just be this. And then I have by De Morgan's law, I have it on the other side. That makes sense to everybody? Why is it the NOR gate? So the I mean, wait, what do you mean? My bad. I meant to write C and D. I was trying to get to here, but so there goes 2 implementations of it. So I mean, it's pretty straightforward from that. Later on, you guys are going to use NOR gates and NAND gates, but for now, I think they just want you to do it with AND gates and OR gates and NOTs. So if you want to do this, then it would be something like this. You would create one for this one. You would create one for this one. And then at the end, you just have to OR them all together. So, you have some kind of OR here. And then, all the inputs go here. Yeah, I mean, this could be something else. Yeah. Well, you have to draw them on the midterm. Most likely, like maybe. I mean, it's not that bad. Just remember, like the and is like semicircle, stuff like that. I wouldn't be surprised if she asked you to like draw a small circuit. Or actually, I think a really popular one is she gives you a circuit and she tells you to like write the expression, the function. So that's not that bad. Like if you have this. This guy here. And then let's say, I don't know if you guys know this yet, but this is an XOR here. This is an XOR. So let's say it's like A, B, C, D, right? I don't know if you guys can see this. So what would be here after this gate? A and B, right? Yeah. And then what would be here? It would be C XOR D. I'll go over this right now, the XOR. And then they're just being ORed together, so you know that the expression is just, this. Right? Okay. So actually, XOR was on your quiz. I mean, if it was on your quiz, I'm assuming you guys had it before. But let me just go over some XOR stuff. So with the XOR, yeah, it's the exclusive OR, like he was saying. So if you have A XOR B, you get this, and then the truth table for A XOR B is just this. So if they're the same, it's 0. If they're different, it's 1. And then from this we can actually write an expression for it, right? Just by taking the DNF form. So F here is equal to this term, which is A prime B, plus this term, which is A B prime. So on the quiz, on the quiz you had something like, you had B C XOR like A, was it A plus B or something like that? Well, whatever. In this case, this would equal just C prime. It's the same kind of thing. You just treat this as like a regular variable, plus C A plus B whole thing prime, and then you would have to do De Morgan's law from there, and simplify it, and then go from there. I feel like. So there's a couple homeworks on this. There's a couple homework problems on XOR, on the like algebraic expressions and simplifying. So memorizing that is gonna be good. I guess I shouldn't have erased it. Whatever. So yeah, A XOR B is equal to A prime B prime plus B prime A. So that's good to know. Same thing with De Morgan's law. Memorize De Morgan's law. So Carnot maps, 2 circuits, truth table to Carnot maps, and all that. So there's another way actually to express like what's happening in your truth table. So another way to express what's happening in a truth table is there's the sum of min terms and the product of max terms, like. There's this notation where F here, I'm gonna go off this. So we know this is the zero position, right? Because and then this is 0, 1, 2, 3. So this can be written like this. It's the sum of the minterms of 0, so 0, this is not a minterm, 2, 3, 4, not a minterm, this is 5, 6, 7, and so on. So that's a way to write it. That's a way to write the information that's on the truth table. Yeah, this is going to be on the homework a lot. And then you know that this is just, if it's the minterm, then you have, if you have 4 variables, then this is A prime, B prime, C prime, D prime. That's the 0 term. The 2 term is, what's the 2 term? Yeah, C what? D prime, right? So C, D prime. And so on. And then you can also write F as the product of its sums of the max terms of the zeros. And then in this case that would just be like F is the product of the max terms, which are here the first max term is 1, so it'd be max term 1, and then there's 2, 3, 4, 5, and 6, right? And so on. That makes sense? So what would be like the expression? Give me these 3. So how would I write this? So when you're writing it in product of sums, if they're primed, if they're zeros, you actually just leave them as is. So the first one would actually be A plus B plus C plus D prime. It's like the reverse of what you do when you're doing this. Does that make sense? So this is I just wrote the 1 term. So all right, what would be the 5th term? The 5 term. So A, say it again. A plus B prime. C plus D prime, right? Yeah, right. That makes sense to everybody? And and so on. You go from there. So that's good. Now there's other things that happen also in a truth table. Like if you're making some function f, a digital function f, and let's say they gave you this thing you have to design, and they're like, okay, this function f is only going to receive odd numbers, something like that. It's never going to receive even numbers. You can be assured that it's only going to receive odd numbers. So let's say it's a 2-bit. Say it's a 3-bit. So it's only going to receive odd numbers. So I'm going to write everything here. 0, 1, 0, 0, 1, 1, 0, or 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. Okay, I think that's everything. So let's say it's only going to receive odd numbers. So let's say this is a 1, this is a 0, this is a 1, and 1. So because it's never going to receive, and let's say it doesn't receive 0 either. Because they told you it's never going to receive these even numbers. These become don't cares. Because you're never going to receive them, so you don't really care what the output is at those combinations of A, B, and C. Does that make sense? That's what the don't cares are about. And the don't cares actually help you simplify your circuit even more. Don't cares because this is 2, right? And let's say like the person that you're making this F gate for tells you you're never going to receive a 2. You're never going to receive 1, 0, 1. So you don't worry about what the output will be at this combination because you're never going to receive it. I'm trying to get the point of don't cares across. So that's what don't cares are about, and they help you out in simplifying your function. So let's say I have A, B, C. So I have 0, 0, 0, 1, 1, 1, and 1, 0, and I have 0, 1. Right? You guys get that? So my 0, 0 mark is, X, it's a don't care, and then it's 1, and then it's another don't care, and then it's 0, and then it's a don't care, 1, don't care, and a 1. So when I'm writing my function f, I can use the don't cares to my advantage to simplify my function f. So in this case, in this function f, I can write it as, this can be a prime implicant, and so can this. And that's valid. That's valid because you won't ever receive these inputs, these combinations, so it won't ever mess up your logic. So you can kind of treat them as they're just being ones. That makes sense? So then here, what's my function f? So for which one? What do you guys? So this prime implicant. What's this prime implicant? It's A. Yeah, it is A, but it's also sorry, it is A. So it's A, and then for the next prime implicant is what? It's B prime, right? Because B prime is the one that's staying constant, A changes, and so does C. So there you go. How simple is that? All you need is A and B prime for your F gate. So that's why don't cares are good. One other thing is, so those are don't cares, and then in notation, when they tell you there's don't cares, you write it in, so what would be my sum of min terms here? What are the min terms? It's, what is it? 157. It's 1, yeah. It's 1. Well, it's actually, it's 1, 5, and 7. So 1, 5, 7. You guys get how we got this, right? And, you also tell it what don't cares you're getting. So you write down the don't care positions also. So what are my don't care positions? 0, 2, 4, 6. Yeah, all the even numbers. Because that was the problem here. And the same goes for the max terms one. So what are my max terms here? What are my zeros?
Wait, but for the don't care?
Yeah.
You only use 3, right?
Yeah. Oh no. I know this is not equal to this. I'm saying that this is coming from the truth table. I'm just writing this all out of the truth table. I'm trying to get you guys used to this notation. This is just the information that they would give me. They would tell you like, oh, F is going to be this. Make a circuit out of it. So what would be my product of max terms? Just yeah, exactly. Just 3 actually. And then I multiply the don't cares, the product of the don't cares. So what would be my don't cares? Same thing, right? The 0, 2, 4, and 6. So this is mathematical. This is the sum. This is a sum. This is a product of. So if you have like the product of x from I to n, this is equal to x, or this is equal to I. I plus 1. I plus 2, and so on. That's what that means. This is the product of sums notation. Okay. So yeah, that's don't cares, and that's the Carnot map, and how you get from one to the other. So what about this? What if I told you I didn't want like the minimum sum of products? I wanted the minimum product of sums from this Carnot map. What would you do? So I want the minimum product of sums, not the sum of products. Yeah, exactly. Instead of doing the prime implicants with the min terms, with the ones, you do the prime implicants with the zeros. So in this case, like the simplest one I can get is this guy here. So what would that be in terms of f? So it's definitely a. Yeah, exactly. A plus b prime, And lo and behold, it's the same thing. Does that make sense? Do you guys see how we got a plus b prime here? All right. Okay, good. So this brings me to another point. Let's say we had this function f, right? And then we made this into a gate. Let's make this a little more interesting though. Let's make it c prime and b, and then let's put an a here. Yeah. So let's say we actually made this gate. We got it fabricated. We added some extra. We added some other thing here. I made this up right now. It doesn't have to do with this, but and then let's call it a gate f, right? So let's say this was the only gate we had to work with, and we wanted to use it everywhere in our circuit. So what I'm trying to get at is that this gate, this function, can be used to implement other operations. Even though f is already this, you can wire this in a certain way, and you can set it up in a certain way that you will get your OR and your NAND and your all that stuff out of it. So think of a way. Okay, first of all, let's start with an easy one. How can I get the f function to do a not? So what can I do to the inputs that will give me a not function out of f? Is it jumping at you by any chance? No? So what if all right, let's say I took my f gate. It's a gate now. I took my f gate, and this is the A input. This is B, C. And what if I tied A to 0? What if I put a 0 there? Because really the ones and zeros are voltages, right? Ones are one is your high rail, and then 0 is like your low rail or ground, right? So let's say I tied it to ground. I would have a permanent 0 there, right? What if I tied C to 1, to VDD, and I only had B coming out? So what would happen to F here, given this expression? So C will be 1 always, so 1 prime. B will be here, A will be 0, and then we have B prime, and then A will be 0. So what does this actually equal? No. What does this actually equal? Huh? It equals B prime, right? So this function in this setup with these nodes tied to these voltages, 1 and 0, this function is now doing a not operation. Does that make sense? All right. How about you guys? How can I get this to do, or I guess whatever. How can I get this to do an OR operation? What would you do to the gate F? I want it to do OR. So, it doesn't matter what inputs they are A, B, or C, but at the end I want this to be an OR function. So what could I do to the inputs? Yeah, right? You can make C1 and so check it out. So you can make C1, right? And so B here, so if we make C1, this goes to 0, right? So we're left with this. B is being primed here, right? But we already know how to make this into a not, right? So why don't we just put a not, before, what I'm saying? Like, why don't we put a not here before it comes in, and then now we get like B prime, and then it gets primed again, and then we're left with A or B. Does that make sense? So now we've made an OR gate. It took two of our F gates, but it doesn't matter. Our functional complete gate is an actual OR. Does that make sense to everybody? No. That's what I meant. Sorry, I meant like there's an F gate that's in the not combination, and so you get A, B, you get B prime. C is 0, so you get A plus B double prime, right? So you get actually A or B. That makes sense to everybody? So this is important. Keep this in mind while you guys are doing the homework. And I mean, this actually happens. Like, XORs can be made of ands and ors, right? What's an XOR? A XOR B is simply just A prime B prime plus B prime A prime. An XOR gate, this can you see it in the expression. It's pretty much a couple of knots, a couple of ands, and an or. Like that's the same thing that's happening here. This F gate. This F gate is we're using the F gates to build OR gates and NAND gates and so on and so on. So what time is it? It's 48. So 2 more minutes. So do you guys have any questions about anything? No questions on the homework? All right. I guess then I'll see you guys next week, and I'll try to have your homework 3 and maybe homework 4 by next week.